But in a situation where you have current coil, in this case, this is an area, right? Now you change it to a current coil, but this current coil, if it has n identical turns, so it means that you wound many turns around this circular shape to make it like a thicker donut, something like that. Okay, if your circular coil has multiple turns and it encloses an area of A, you can determine the magnetic flux still using the same formula, VA cos theta. So you get the magnitude of the magnetic field strength. You multiply by the area enclosed by this wire over here, which is A. Okay, then cos theta, you get the angle in between the area vector and the magnetic field. In this case, the magnetic field is pointing into the page. The area is also pointing into the page, so the theta should be 0. They are in the same direction. Both the area vector and the magnetic field are pointing into the page. That is magnetic flux. Okay, magnetic flux, when you're calculating magnetic flux, you're calculating for one single turn. Okay, that's the ideal magnetic flux. Even though you have multiple turns, when you calculate magnetic flux, you're only calculating for one single turn. If you want to calculate it for the whole current coil consists of n identical turns, then what you're calculating is called a magnetic flux linkage. Means you link together the magnetic flux through each of the circular loop. There are n circular loops, right? You link together their magnetic flux, then you get magnetic flux linkage. So for magnetic flux linkage, the symbol will be capital phi. Previously, this is small phi. If it's capital phi, you can see I put a capital I with a circle inside it. Okay, so capital phi can be determined just by taking the magnetic flux that you learned earlier and multiply by the number of turns that you have. So it's just n times the dot product of magnetic field and area vector. Again, n is the number of turns around this enclosing this area over here. Okay, so you can break it open, then it become the number of turns multiplied by the magnetic field strength multiplied by the area multiplied by cos theta, and still theta is the angle between the magnetic field and the area vector. Okay, so this magnetic flux linkage is for the whole current coil, but magnetic flux is only for one single turn. Okay, so these two things you need to be able to differentiate it well. And there's another terms that you might encounter it in the last chapter, and I'm going to revisit it right now. And the term is called magnetic flux density, and it's represented by the symbol of B, which is the same as the magnitude of the magnetic field, which is magnetic field strength. Okay, magnetic flux density, the idea is that it's a magnetic flux per unit area. Okay, you learn about density. Density is mass per unit volume, right? But in this case, there's only a plane. It's not a 3D thing. It's just a plane. So it's a per unit area calculation. Remember, density is mass per unit volume per unit something. Okay, so the density here is per unit area. There's no 3D shape, so it's per unit area. So you learn that magnetic flux density is the magnetic flux per unit area, but this area has to be perpendicular to the magnetic field. So now we know that magnetic flux density is just our phi, our magnetic flux per unit area, and the area have to be perpendicular to the magnetic field. And you know that the area perpendicular to the magnetic field is just cos theta, A cos theta. You might think perpendicular might be sine, but remember when we talk about theta, it's the angle between the area vector and the magnetic field. The area vector and the magnetic field in this diagram over here, they are both in the same direction, so their theta is 0. But the angle between the, let me be more clear over here. The magnetic field is pointing into the page, okay, and the area vector is also pointing into the page. So the angle between these two vectors is 0. So this is cos 0 degree that you substitute it inside here. Okay, but when I say, when you try to find A perpendicular, why do you use cos theta? Usually perpendicular is sine, right? It's because this cos theta here is the angle between B and A and it's 0 degree. Usually when we say perpendicular, the angle is between the plane and the magnetic field, and that is 90 degree. So it's sine 90 degree, but it's equivalent to cos 0 degree. So this one is cos theta because it's the angle between the area, it's the angle between the area vector and the magnetic field. It's not the angle between the magnetic field and the plane of the area. Plane of the area and the magnetic field is indeed 90 degree. And if you want to find the area perpendicular, you should do sine 90 degree usually. But now this cos theta here, this theta is representing the angle between the area vector and the magnetic field. It's not between the plane. It's not between the plane and the magnetic field. So this one you have to be more careful. It's cos theta. That's why if you take phi divided by a cos theta, you shift this thing around, you get b back. So it's just magnetic flux density is just magnetic field strength. Basically, if you can't understand this part, you just need to know that magnetic flux density, the density means per unit area. And because you know that it's per unit area, you take the phi divided by the area, you get back the magnetic field strength. So magnetic flux density is just the magnetic field strength. Okay, so these are a few terms that you need to know their meaning.